Hello class, we're going to talk about exponential relations or functions, and we've been talking about a little bit about them already in the past couple of days, but what is it really in general? And focus on the very top of your handout. It's either y, or here it says f at x, and think about it as y equals b to the power of x. So b has to be a number that's larger than 0, cannot equal to 1, and x is any possible real number. So when you say real number, that means a number not just whole numbers like 1, 2, 3, 4, 5, or negative 1, 2, 3, 4, 5, but also 0.1 or negative 0.2. So this time we've looked at things before where x is just, the variable x has just been a normal number, x has been the base to squared, so y equals x squared. Now we're going to putting the x in the power instead of on the base. So the example there of what does an exponential function look like on a graph and on a table of values. So on the table of values, focusing on that, you can see that x equals 0, 2 to the power of 0 is always 1, and with y equaling 2 to the power of x, you can see it's less than 1 but bigger than 0 even when x is negative 1, negative 2, and it grows exponentially as you see from 1 to x equals 1, 2, and 3. On a graph you can see it more clearly. You see any numbers where x is equal to negative 1 and to the left, it approaches 0, but you can't really tell. And then when you go beyond 4, it goes off this graph when x is positive 1, 2, 3, and 4. So there it is. Most exponential graphs resemble this same shape. Graph's very, very small on its left side, very close to the x-axis. As the graph progresses to the right, it grows faster and faster and shoots off the top of the graph very quickly. In a straight line, the rates of change remain the same across the graph. In these graphs, the rate of change increases or decreases across the graphs. Other characteristics, I'll read them out loud. For y equals b to the power of x, or here it says f at x, the graph crosses at the y-axis, that's 0, 1 all the time. When b is larger than 1, the graph increases. When b, the base, is between 0 and 1, the graph decreases. The domain is all real numbers, so all x values is all real numbers. The range is all positive real numbers. It's never 0, it's never negative. The graph passes the vertical line test, so therefore it's a function, not just a relation, but it's also a subsection called a function. We'll talk about that maybe at another time, but think about more as a relation than a function. The graph passes the horizontal line test, so its inverse is also a function. The graph is called asymptotic to the x-axis. It gets very, very close to the x-axis, but does not actually touch it or cross it, even though, to the contrary, it looks like that. Let's move in. So if you go to your into your book, page 382, they ask you to do graphs of exponential relations. Well, you don't have a graphing calculator. I'm going to try to set this up. I'm just going to go turn this on. Find the right lighting here. And go y equals, and they want y equals 2 to the power of x. So I've been using these for a while, so let's try to find letter x. There it is. To the power x. and y equals 4 to the power of x. So let's just graph 2 to the power of x in the first place. And there's 2 to the power x like we had on your handout. Now what happens if we also plot 4 to the power of x? So the number gets big, if the base gets bigger, there's not much difference looking on the graph. There's not much difference on the graph over there on the left-hand side, as you can see. But on the right-hand side, you can see that 4 to the power of x moves up quicker than 2 to the power of x. So the bigger the base, the faster it moves up vertically on the right-hand side of the graph. They're going to ask you to make graphs, make a table of values and graph each relation in general, but more work on making a table of values of how to find 2 to the power x, 3 to the power x, half to the power of x. So even the base can be less, remember, less than 1, but larger than 0. And what are the similarities and the looks like we talked about what happens when there's bigger than 2, 2 and 4, 2 and 3, but there's half. So the table of values on the left-hand side and on the graph, you can see the difference. That on the left-hand side, when the value of b, which is in this case a half, is less than 1, bigger than 0, it looks like that the exponential function is the mirror opposite. So that means its number is really high when x is in the negative section, negative 4, 2, 3, and it starts decreasing very quickly. It crosses that 1, that y, when x equals 0, y equals 1 still, and as it crosses the right-hand side, you see it the y values approach 0 as x gets bigger in positives, 1, 2, 3, 4, 5, and beyond, but never actually reaches 0. So I try to sharpen it. There we go. But here's the problem that we want to really work on. I don't want you to be afraid of these questions just because they're big numbers. So example 2, population growth. You can read it there. Ontario's population is projected to grow exponentially based on the relation p equals 11 million times 1.0112 to the power of n, where p is the estimated population and n is the number of years after 1996. The formula is expected to be valid until 2031. 1, they want you to sketch a graph of this relation. And b, what was Ontario's population in 1996, shown in this graph. C, what was the projected population for Ontario in 2031. So there's the sketch, quote unquote, number of years after 1996 and the population on the y-axis. And there's your table of values. I'm like, what in the world? How do you get all these numbers? Well, B shows you how. So in a relation, n is the number of years after 1996. So for 1996, n equals 0. So there's no years after. So the population, so any number to the power of 0 is 1. So just 11 million. And C, the year 2031 is 35 years after 1996. So you replace n equals 35. So then you have to do 1.01.12 to the power of 35 before you multiply it to 11 million. And it's like, okay, how are we going to do that? Well, you know what? I'm going to have to hold back and show the answer in the next video.